The next in-class problem actually is a little bit of a harder problem for determining the equilibrium constant because it requires an ICE table to calculate equilibrium concentrations. So I'm first going to go through this sample problem here on how to create an ICE table. So if this is confusing for you, you want to make sure to watch this video so that you understand how to create an ICE table. So an ICE table, which stands for Initial Change Equilibrium, it's basically just a method to keep track of materials that are participating in an equilibrium reaction, and it's going to become a critical part of our strategy for solving equilibrium problems. So this worksheet is going to work through how to set up a reaction table. We're going to look at it for 2 reactions here, and so we're going to walk through writing reaction tables for both of these. So I'm going to kind of split my paper in half here, and I'm going to do A on the left and B on the right. And we're going to walk through this step by step for each of these reactions. So the first thing you want to do when you write a reaction table, an ICE table, is write your equation on top. And we want to make sure it's a balanced equation. Since this is just a kind of a generic equation, we don't necessarily know if it's balanced. So we're going to assume that they gave us a balanced equation. Step 2. Allow for 1 column for each species in the equation, but solids and pure liquids are omitted. So we can see for this first hypothetical equation, we're having 2 molecules of gaseous A combined with solid B to form 3 C molecules. Because B is a solid and it's not going to appear in our reaction quotient or our equilibrium expression, I'm going to draw a vertical line here so that I know not to put anything in that column because it's not part of our equilibrium calculations. So our balanced equation goes on top. We're going to leave columns for each species in the equation with the omission of solids and pure liquids that don't appear in our equilibrium expressions. We're going to allow for 3 rows in our ICE table. The first row is going to be for initial reaction conditions, which are going to be concentrations. The next is going to be a consideration of how they're going to change. And lastly, where things end up when we reach equilibrium. So you just write ICE down the left-hand side. The fourth step is to add in initial values provided in the problem, making sure to use proper units in terms of either molarity or atmosphere. Again, you'll use molarity if you're talking about a Kc value. You'll use atmosphere if you're talking about a Kp value. Now, this problem really didn't give us any amounts here. So what I'm going to do is I'm going to assume maybe for this first reaction that we started with, say, 1 molar A and 0 C, no product. Information provided is going to tell us that Q is less than K. If I set this reaction up like this, where I start out with a certain amount of material as A and no product, my Q is less than K. I'm not where I want to be, and my reaction will shift to the right. So step 5 reminds us that the most error-prone step in determining change values is, the most error-prone step in this process is determining what these change values are. So change values in an ICE table are always going to be variables. They're going to be x's, okay? These x's will have coefficients that match the coefficients in the balanced equation, and they will have signs who indicate the direction of the reaction. So if something's disappearing, we're going to have it as a minus sign. Well, because Q was less than K for this reaction, and we know it can only shift to the right because we have none of our product, that means some of my A is going to disappear. So I'm going to write a minus 2x here. I don't know how much it's going to disappear. I'm just going to write it as an x, but this coefficient needs to come down and become part of that. Anything that's appearing, you can write a plus if you want, or you can just leave it without a sign to indicate that it's positive. So again, if a substance is disappearing, add a minus sign, positive it's appearing, and again, we may need to compare Q with K to determine which way the reaction is proceeding. This tells us that Q is less than K, so we are not at where we want to be. To make Q be larger so it approaches K, that means we have to shift to the right and make products. In my hypothetical reaction here, I said, let's imagine that we've got no product. So there's only one way that this reaction can shift. Coefficients, again, from your balanced equation are propagated into these variables here. So this means that this is 2x. Here we've got 3x. Step 6 says fill in the equilibrium values. I like to write kind of a sum line here. Fill in equilibrium values by summing the initial and change columns. So we're going to have 1 minus 2x and then 3x. The point is, these don't tell us actual concentrations. They tell us that we're going to have 1 molar minus some amount multiplied by 2, and 3 times that some amount. And again, that 3 and that 2 are given by our reaction stoichiometry, but we don't know how much that is. So part of what the rest of the sample problems are going to involve is how we calculate these equilibrium concentrations by solving for K. So step 7 just tells us for ice tables, additional information, an equilibrium constant. Maybe they give us one of the species at equilibrium so we can set this equal to that. Something will allow us to solve for X. It may be something where we need to make some simplifying assumptions, or maybe in the worst case scenario, need to use the quadratic equation to solve this algebraically. So here's how we'd set up an ice table for our first hypothetical reaction. Let's set up our second one, and I'm going to go through it, not walking through step by step. I'm just going to look at the chemical equation and set it up. So we set up our ice table by first writing our chemical equation on top. We write ICE down the side. I don't have any solids or pure liquids, so everything's going to appear in my equilibrium expression here, and everyone will appear in my ice table. I'm going to assume that I have some values here, let's say A, B, and C amounts. I don't know what they are, but information that's provided within a problem here will tell me that Q is greater than K. When Q is greater than K, that means I am product heavy. That tells me my reaction needs to shift to the left. I need to make more reactants. That means I'm going to be making more D at the expense of using up A and F. I'm sorry, E and F. So what this means, there's no coefficient in front of D, so this is just going to be plus X. This is going to be minus 3x, and this is going to be minus 2x. And just as a reminder, I know that I'm going to be making more reactant because something in my problem told me that Q was greater than K. Maybe it was something they told you outright. Maybe it was the fact that I had 100% product and this was a 0. Then the only way I could shift is to the left. Or maybe it's something where they actually gave me concentrations of all the species that I have here, and I put it into my equilibrium expression. I put it into the reaction quotient, and I mathematically calculated what Q was equal to and compared it to K. Again, propagating this through, my equilibrium concentration of D is going to be some value A plus a little bit. E is going to be what you started with minus 3 times that little bit. And F is going to be C minus 2 times that little bit. If we want to find what that little bit is, we need to use some basic algebra and some other pieces of the problem that are given to us. So we'll work on those through the next few sample problems.